Everything you see is made of atoms. Your phone, your body, the air you breathe. But inside those atoms is energy. More energy than you can imagine. This is the science that powers cities and changed the course of history. Welcome to Atomic Archives. Let's start simple. What is an atom? An atom is the smallest unit of matter that keeps its properties. At the center is the nucleus, made of protons and neutrons. Protons have a positive charge, neutrons have no charge. Orbiting around the nucleus are electrons. They have a negative charge. This structure is held together by fundamental forces. The electromagnetic force keeps electrons in orbit, but in the nucleus, something stronger is at work, the strong nuclear force. It binds protons and neutrons together, and it's incredibly powerful. This force is what nuclear energy taps into.
1896. Henri Becquerel was studying phosphorescence in uranium salts. He left the uranium on photographic plates in a drawer. When he developed the plates, they were fogged. The uranium was emitting invisible rays, even in complete darkness. He had discovered radioactivity. Marie and Pierre Curie took this further. They isolated polonium and radium, both intensely radioactive. Marie Curie coined the term radioactivity, and she paid for it with her life. Her notebooks are still radioactive, over 100 years later. But their work showed us that atoms aren't stable. Some decay, release energy, transform into different elements. This was the key to understanding nuclear energy. 1938. Otto Hahn and Fritz Strassmann bombarded uranium with neutrons. They expected the uranium to absorb the neutrons. Instead, they found barium, an element much lighter than uranium. The uranium atom had split. Physicist Lisa Meitner realized what happened: nuclear fission. When a uranium-235 atom absorbs a neutron, it becomes unstable. It splits into two smaller atoms, releases energy, and fires out more neutrons. Those neutrons can hit other uranium atoms, creating a chain reaction. This was the discovery that changed everything, because if you could control the chain reaction, you had a power source. If you couldn't control it, you had a bomb.
A nuclear chain reaction happens when each fission event triggers more fission events. One atom splits, releases 2 to 3 neutrons. Those neutrons hit 2 to 3 more atoms, which split, release 4 to 9 neutrons. The reaction multiplies exponentially. In an uncontrolled chain reaction, this happens in microseconds. 1 kilogram of uranium-235 undergoing complete fission releases the same energy as 20,000 tons of TNT. This is a nuclear weapon. But in a controlled chain reaction, we regulate the neutron flow. We use control rods made of materials that absorb neutrons. Push them into the reactor core, the reaction slows down. Pull them out, it speeds up. This precise balance is what makes nuclear reactors work, and what makes them dangerous when that balance is lost. A nuclear reactor is essentially a very sophisticated kettle. Here's how it works. Uranium fuel rods are arranged in the reactor core. Nuclear fission heats the fuel rods to over 300 degrees Celsius. Water circulates through the core. It absorbs this heat. In a boiling water reactor, this water turns directly to steam. In a pressurized water reactor, the hot water heats a secondary water loop. Either way, you get high-pressure steam. The steam spins a turbine. The turbine spins a generator. The generator produces electricity. After passing through the turbine, the steam is cooled back to water, and the cycle continues. One uranium fuel pellet, the size of your fingertip, contains the same energy as 1 ton of coal. This efficiency is why nuclear power is so attractive, and why we keep building reactors despite the risks. Not all radiation is the same. There are 3 main types we need to understand. Alpha particles. These are helium nuclei, heavy and slow. They can't penetrate skin. A piece of paper stops them.
But if you inhale or ingest an alpha emitter, it's extremely dangerous. Beta particles. These are high-speed electrons. They can penetrate skin, but are stopped by aluminum foil. Moderately dangerous externally, very dangerous internally. Gamma rays. Pure electromagnetic energy. They penetrate everything. You need thick lead or concrete to stop them. Extremely dangerous. This is what killed many Chernobyl firefighters. Each type of radiation damages biological tissue differently. They ionize atoms in your cells, break chemical bonds, damage DNA. Low doses, your body can repair the damage. High doses, the damage is catastrophic and irreversible.
We measure radiation in several ways.
Becquerels measure activity, how many atoms decay per second. Grays measure absorbed dose, how much energy is absorbed by tissue. But the most important unit is the sievert. Sieverts measure biological damage, the health impact of radiation. Here's a reference scale. A chest X-ray, 0.02 millisieverts. Background radiation per year, 2 to 3 millisieverts. Pilots and flight crew, 5 millisieverts per year. Cancer treatment dose, 20,000 to 80,000 millisieverts, targeted to the tumor. Acute radiation sickness starts at 1,000 millisieverts. 50% lethal dose, 4,000 to 5,000 millisieverts. The Chernobyl firefighters received 6,000 to 16,000 millisieverts. Understanding these numbers helps us understand the risks and why radiation safety protocols are so strict.
Not all uranium can fuel a reactor. Natural uranium is 99.3% uranium-238. Only 0.7% is uranium-235. But uranium-235 is what we need for fission. So we enrich uranium, increase the concentration of U-235. Reactor-grade uranium, 3 to 5% U-235, enough for power generation. Weapons-grade uranium, 90% plus U-235 for nuclear weapons. The enrichment process is complex, expensive, tightly controlled, because it's the same process for both power and weapons. Then there's plutonium. Plutonium-239 doesn't occur naturally. It's created in reactors. When U-238 absorbs a neutron, it becomes Pu-239. Plutonium is even better for fission than uranium. This is what powered the Nagasaki bomb. And it's why spent nuclear fuel is so dangerous and valuable. It contains plutonium, which can be extracted and weaponized. Nuclear power has one massive problem: waste. After uranium fuel is used in a reactor, it's still highly radioactive. It will remain dangerous for thousands of years. Plutonium-239, half-life of 24,000 years. Uranium-235, half-life of 700 million years. We generate about 12,000 tons of nuclear waste per year globally. Where do we put it? Current solution: temporary storage pools at reactor sites. The spent fuel sits underwater. The water cools it and shields the radiation. But this was only supposed to be temporary. We need permanent geological repositories, deep underground, in stable rock formations. Finland is building Onkalo, the world's first permanent repository, 500 meters underground, designed to last 100,000 years. But most countries? Still storing waste on site, waiting for a solution that may never come. This is the 10,000-year problem we've created. The reactors operating today were designed in the 1960s and 70s. But nuclear technology hasn't stood still. Small modular reactors, factory-built, safer, more flexible. They can't melt down because they use physics, not active systems, for cooling. Thorium reactors, using thorium-232 instead of uranium. More abundant, less waste. Can't easily be weaponized. Fast breeder reactors. They consume their own waste, creating more fuel than they burn. And then there's the holy grail, nuclear fusion, the power source of the sun. fusing hydrogen atoms into helium, releasing massive energy, no meltdown risk, minimal radioactive waste, unlimited fuel from seawater. We've been 30 years away from fusion power for 60 years, but recent breakthroughs at ITER and NIF show it's getting closer. Nuclear energy isn't going away. The question is, can we make it safe enough, clean enough, to power our future? This is Atomic Archives. Diagram, educational illustration, clean design, labeled parts, scientific accuracy, modern textbook style, clear lines, professional. Archival photograph style, black and white or period-appropriate color. Documentary quality, historically accurate. Facility equipment, modern industrial photography, high detail, professional cinematic lighting, clean, technical. From Becquerel's discovery to fusion reactors. From Hiroshima's destruction to carbon-free power. Nuclear science is humanity's most powerful technology and our most dangerous. Understanding it isn't optional anymore, because the decisions we make about nuclear energy will shape the next century. This is Atomic Archives, where we explain the science, document the history, and explore the future of atomic power. Subscribe for more.